Okay, so this is part 2 of the video. Now, in part 1, we just looked at cis without any modulus. So the modulus was just 1. What we're going to do now is bring in the modulus and see what that does. So I'm going to have two made-up imaginary numbers, one called z, and that's going to be equal to the modulus of z times cis theta, and one called w, which is the modulus of w times cis of phi, this other Greek letter. And we're just going to multiply them together and see what happens. Okay, so if we do z times w, we're just going to substitute directly from what's above. So mod z cis theta times mod w cis phi. Now, because we're just timesing stuff together, we can actually rearrange that and we can put the mod z and the mod w out the front. And then we've got cis theta and cis phi coming after that, okay? So what this means is that if we look at this part here, we know from our rules for cis that we can just do theta plus phi, okay, and combine them together. So this is kind of the key point. When we multiply z by w, we just end up with the two moduli out the front being multiplied together. And this actually gives us the modulus of the new complex number. This is the bit out the front. So this is actually the modulus of z times w. Then we have cis, and then we have theta plus phi, which is just the two arguments added together. So this bit here is just the argument of z times w. So the key idea there is if we multiply two complex numbers when they're in polar form, then we multiply the moduli and we add the arguments together for our new complex number. Okay, hopefully that makes sense. So can you just pause the video and write down at least what's in the green and the orange squares there? You may want to add in these notes here as well. Let's just have a think about what that means on the eigenplane itself. Okay, so when we actually look at what that does, well, let's say here was z, and here is w. They kind of look like they're at right angles. That's not necessarily always going to be the case, but so here's theta. Theta's that angle there, and then phi is going to be that angle there. Now, if we multiply them together to get zw, then what we're going to be doing is we're going to be adding those two angles together. So we're going to end up with phi plus theta for our new complex number. Okay, so that's roughly where it'll be. And then we're going to be multiplying these two lengths. So the new length, assuming those lengths are greater than 1, is going to be somewhere out here. So whatever the lengths are going to get multiplied together for the new complex number. So we can kind of think of this like two different geometric transformations. The first transformation, when we multiply by w, is that we're going to rotate by this angle phi. The second geometric transformation is a dilation, and the dilation that's like stretching, okay? It's stretching it. The dilation is going to stretch by whatever the modulus of w is. Hopefully that kind of makes sense. Let's just do a quick example on that. So let's say we've got z and it's 2 cis, 2 pi and 3. We want to find the modulus and argument of negative I times z. Well, we could sort of break it all down into our usual Cartesian form and multiply it out that way, and that would be very long-winded. But now that we know what we know about multiplying in polar form, we can do this very, very easily. So what we're going to do is we're going to use the fact that negative I can be put into polar form itself. So negative I, if we put that into polar form, well, the modulus of, actually, if we just look at the Argand diagram, negative I is over here somewhere. sorry, not there. Negative I is down here. Okay. It's got a modulus of 1. There's only 1 long. And the angle, the argument to get there is negative pi over 2. So we can just put it into polar form as the cis of negative pi on 2. So then since we're multiplying z by that, we can say, okay, negative I times z is just what we've got above, the cis of negative pi on 2, multiplied by our value for z. Now, because we know the rule for multiplying complex numbers in polar form, what we're going to do is we're just going to multiply together the two moduli. The moduli there is just 1, so the new modulus is 2. And then we're going to take the cis and we're going to add together the two arguments. So the negative pi over 2 and the 2 pi and 3. I've just flipped the order there because it makes more sense to have the negative second, but we're just adding those two together. 1's over 3 and 1's over 2, so we need to do a bit of fractions, get them both over 6, so 4 pi over 6 minus 3 pi over 6. All I've done there is multiply that one by 2 and 2, and that one by 3 and 3. So 4 pi over 6 minus 3 pi over 6, and we end up with 2 cis pi on 6. So what this has done, so if we look at what that does on the eigenplane, well, we've got our value here, negative I. 2 pi over 3, so 2 cis 2 pi over 3 is up about here somewhere. 2 cis 2 pi over 3. When I multiplied that by negative I, what it did was, since this angle is negative pi over 2, it actually brought my answer back around to here, which is 2 cis pi over 6. So it actually rotated z, this is z, it rotated it by negative pi over 2. So when I multiplied by negative I, it caused that rotation. The modulus was only 1, so it didn't actually change the modulus. But if the modulus was bigger, for example, then it may have extended that that vector. Okay, so hopefully that example makes sense. I'll definitely be copying that one down into your book. So I'll just give you a moment to pause and do that. And let's just sum up. So why is polar form so useful? That was what we were setting out to find out. This is, one of the main reasons why polar form is so useful for us. The first one is that it allows us to easily divide and multiply complex numbers. It's really, really straightforward. You just multiply the moduli, add the arguments, and you're good to go. The second reason is the geometric reason. So when you multiply by this complex number, if it was z, then we can think of that as a geometric transformation that causes a rotation by whatever the angle is. So whatever theta is how much it will rotate by, and a dilation by this factor mod z. Dilation, remember, means stretching or shrinking. So if z was, say, a half, then it would actually shrink it. If it was 2, 3, 4 or whatever, it would make it longer. Alright, thank you very much for watching. I hope that makes sense. Please message me if you have any questions at all.